In this session, we study some issues in selection of independent variables, when we use regression analysis for investigation of causal relationships. This is actually a topic of data analysis methodology in empirical sciences, such as epidemiology, econometrics, psychometrics, and biometrics, rather than a topic of statistics. Statistics deals with variations in values of variables, not causal relations among them. In our program, this topic is studied in more depth in epidemiological method courses. But this is a course in applied statistics, and basic understanding of this topic is needed when we apply statistical methods to substantive research. In particular, understanding of topics in this session is needed for research note assignments of this course. This session has two major learning objectives. First, we study different types of variables in the context of causal relationships. Specifically, we study the distinction among the dependent variable, its determinants, confounders, mediators, and outcomes of the dependent variable. Second, we study how to properly select independent variables when the regression analysis is used for an investigation of causal relationships among variables. Corresponding to the major objectives, this session is divided into two sections. In the first section, we study several types of causal relationships among three or more variables, and in the second section, we study some basic guidelines for selecting independent variables. We mainly think of a situation in which our focus is on causal relationships between two variables of our interest. Here, they are denoted as x1 and y, and suppose we are interested in the causal effect of x1 on y. In such a case, if we have data on x1 and y, we look at the statistical association between x1 and y, because their statistical association should reflect their causal relation. But some other variables may be causally related to x1 and y, as confounders, mediators, outcomes of y, or in some other ways. They may also be related to x1 and y as effect modifiers, which we will study in a later session on interaction. In this diagram, the green arrows indicate the causal effect of x1 on y, which is the relationship of our major interest. Another variable, x2, is related to x1 and y, as a confounder. In the upper diagram, x2 has causal effects on both x1 and y. In the lower diagram, x2 is associated with a factor that has a causal effect on x1, and a factor that has a causal effect on y. Both factors are indicated as question marks. More accurate definitions and more detailed descriptions of confounder are given in epidemiological method courses, but this is enough for the purpose of this course. A very important thing is, if there is a confounder x2, then the statistical association between x1 and y does not only reflect the causal effect of x1 on y, but also the combination of the causal relation between x2 and x1, and the causal relation between x2 and y. In this example, we are interested in causal effects of education on systolic blood pressure, because, for example, education may help people to learn more about health and diseases, and therefore raise people's concern about health promotion and disease prevention. But as shown in the lower diagram, gender may be a confounder. Females and males are physiologically very different, which may affect their cardiovascular health. Age may be a confounder as well. The aging process may affect blood pressure. For the majority of people, their accomplishments in formal school education remain unchanged after age 25, so adult age seems to have no effect on the level of school education. But age at a given time indicates the cohort to which the person belongs. Younger people belong to more recently born cohorts. As the education system developed and expanded in recent decades, those in younger cohorts tend to have higher educational levels. So, gender and age may be confounders of the causal relation between education and systolic blood pressure. The statistical association between education and systolic blood pressure may reflect not only the causal effect of education on systolic blood pressure, but also effects of age and gender on education and systolic blood pressure. Interestingly, confounding effects of gender and age may be in the opposite directions. Education should have a negative effect on systolic blood pressure. Those with higher educational levels tend to have lower systolic blood pressure. Probably age strengthens the negative association further, because those in younger generations tend to have higher levels of education, and younger people tend to have lower systolic blood pressure. But gender may weaken the negative association between education and systolic blood pressure if males tend to have higher blood pressure than females. In this case, gender makes education and systolic blood pressure more positively associated with each other, whereas the causal effect of education on systolic blood pressure makes them negatively associated with each other. In such a case, gender is considered a suppressive confounder. This table shows estimated regression coefficients of education categories from 2 regression analyses of systolic blood pressure. In addition to education as an independent variable, Model 1 included gender as well, and Model 2 included both gender and age. The results of Model 1 show a fairly strong negative relationship between education and systolic blood pressure. It is estimated that on average, people who have not graduated from high school have 9 points higher systolic blood pressure than college graduates, and high school graduates have 5 points higher systolic blood pressure than college graduates, adjusting for gender. Model 2 included age in addition to education. The statistical association between education and systolic blood pressure is still strong. It is estimated that people who have not graduated from high school have, on average, nearly 8 points higher systolic blood pressure than college graduates, and high school graduates have 4 points higher systolic blood pressure than college graduates, adjusted for gender. The estimated regression coefficients in this table are statistically significant at the 0.05 level. But the negative association between education and systolic blood pressure in Model 2 is weaker than that in the Model 1 results. This is because age has a confounding effect of strengthening the negative association between education and systolic blood pressure, and the confounding effect was removed from the association by including age in the regression model and adjusting the association between education and systolic blood pressure for age. If you are investigating effects of education on systolic blood pressure, should age and gender be included in your regression model? The answer is generally yes, because regression coefficients for education categories should reflect the relation between education and systolic blood pressure, adjusted for gender and age, that is, the association between education and systolic blood pressure among people who have the same gender and the same age. In general, if you are investigating causal effects of X1 on Y, confounders should be included in your regression model of Y, as additional independent variables. Another important type of variables in causal relationships is a mediator. This diagram may look like that for confounder, but the direction of causal arrow between x1 and the third variable, denoted here as x3 instead of x2, is opposite to that in the previous diagram. So here, x1 affects x3, and then in turn, x3 affects y. It can be considered that, in the pink pathway, the effect of x1 on y works through x3. Conceptually, total mediator and partial mediator are distinguished, and x3 in this diagram is a partial mediator, in that x1 affects y partly through x3, but partly without going through x3. If all effects of x1 on y go through x3, this diagram would not have the green path, and x3 would be considered a total mediator. But in most cases in which a plausible mediator is identified in actual data analysis, it is a partial mediator. Here, it is hypothesized that education raises the concern about the importance of healthy lifestyles, thus those with higher education levels tend to do more exercise, which helps them to control their body weight. In this case, exercise is considered as a mediator between education and BMI. This table shows estimated regression coefficients of education categories from 2 regression analyses of BMI. In addition to education as an independent variable, Model 1 included age and gender. Model 2 included age, gender, and physical activity. The results of Model 1 show a negative association between education and BMI. Both the difference between those who have not graduated from high school and those who have graduated from college, and the difference between high school graduates and college graduates, are statistically significant at the 0.05 level. The pattern is a little complicated, in that the middle group, high school graduates, tend to have the highest BMI, controlling for age and gender. In Model 2 results, the association is weaker than that in Model 1 results, that is, the estimated average difference between those who have not graduated from high school and those who have graduated from college became smaller, and so did the estimated average difference between high school graduates and college graduates, and p-values for those differences became larger. This change between Model 1 and Model 2 results is consistent with the hypothesis that the effects of education on BMI are exerted partly through physical activity. Another type of variables related to causal relations between two variables is an outcome, or results, of the dependent variable. In this slide, x1 affects y, and then y affects x4, so x1 affects x4, through y. Therefore, x4 is an outcome of y. In this example, The focus is on causal effects of education on blood glucose. And an increased level of blood glucose raises the risk of diabetes. Education is X1, blood glucose is Y, and diabetes status is X4, which is an outcome of the dependent variable. The upper diagram shows this causal chain. The lower diagram indicates what regression coefficients of education categories would show if a regression analysis of blood glucose, including diabetes status as an independent variable, is carried out. The coefficients of education categories show the association between education and blood glucose, controlling for diabetes status, i.e., the association between education and blood glucose among people who have the same diabetes status. So, the inclusion of diabetes status splits effects of education on blood glucose into two. The first is effects of education on blood glucose that in turn affect diabetes status. This is displayed as a pink pathway. The second is effects of education on blood glucose that do not make a difference in diabetes status. This is indicated as a green pathway. The regression coefficients of education categories reflect only the green pathway, but not the pink pathway. Therefore, the regression coefficients capture only a part of causal effects of education on blood glucose. This table shows estimated regression coefficients of education categories from two regression analyses of blood glucose. In addition to education as an independent variable, Model 1 included age and gender as well, and Model 2 included age, gender, and diabetes status. The results of Model 1 show a strong association between education and blood glucose. The p-value for the difference between those who have not graduated from high school and those who have graduated from college is very low, and the p-value for the difference between high school graduates and college graduates is quite low. The inclusion of diabetes status made the association between education and blood glucose in Model 2 results weaker than that in Model 1 results. The estimated average difference between those who have not graduated from high school and those who have graduated from college became smaller, and so did the average difference between high school graduates and college graduates, and p-values for those coefficients became larger. In this case, it is difficult to consider this change as a result of control of confounding effects of diabetes status, because it seems reasonable to think that the level of blood glucose affects the risk of diabetes, not the other way round. So, the regression coefficients in the Model 2 captured the effects of education on blood glucose as far as they do not make any difference in diabetes status. Probably, the Model 2 regression analysis captured just a limited portion of education's effects on blood glucose. This is a special case of causal chain involving an outcome of the dependent variable. X4, an outcome of Y, in turn, affects X1, so the causal chain becomes circular. In such a case, it is quite difficult to estimate strengths of these three causal arrows, separately from each other. Suppose you are investigating causal effects of X1 on Y, using regression analysis. In addition to data on X1 and Y, you have data on another variable, Z, and you think Z may be related to X1 and or Y in some ways. Z may be a confounder, mediator, or a result of Y, and you are not sure which one. In that case, you should ask two questions. The first question is Z likely to affect X1, or is X1 likely to affect Z? The second question is Z likely to affect Y, or is Y likely to affect Z? The combination of your answers to the two questions help you to choose a likely role of Z for the causal relation between X1 and Y, as indicated in this table.